Good morning, everyone. Namaste. This is Dr. ANANDA BABU, Associate Professor, Department of Mechanical Engineering. I welcome you all to the second session on digital manufacturing. The course started on May 29th and it will continue up to June 2. Okay, good morning. We will continue the session. This is the second session. And first, before going this session 2, we will just recap whatever the topics we have discussed in last class, session 1. In session 1, we have discussed what is digital manufacturing and what are the elements or the building blocks of the digital manufacturing and how it will help the customers for the required components, how to satisfy the customer with the prototype and the quality based on the demand of the customers. And we have learned, we have gone through the various building blocks of digital manufacturing. Among additive manufacturing is one of the key parameters through which we can prepare the prototypes or tooling before manufacturing the final components. And we have gone through the subtractive manufacturing. We have gone through what is subtractive manufacturing and what is additive manufacturing. And we have gone through the overview of the global AM market. And in India, the global market percentage is 3 to 5% only. And in this aspect, the usage and the involvement and the development of additive manufacturing has to be geared up in India. And what are the different additive manufacturing drivers in revenue point of view? We have seen, and government initiatives recently, the government initiatives are more to promote and to encourage the additive manufacturing sector in industry, academia, and automobile, and so many fields. And we hope we will get more initiatives and more schemes from the government side. And we have seen the comparison of product development cycle of the additive manufacturing products and the injection molding. And by using this additive manufacturing and a digital filing system, we are able to complete the development cycle, product development cycle within days as compared to the within weeks or months of the injection molding. The time, the delay in the injection molding are the number of steps we have to take to prepare a component. In the product development cycle point of view, the injection molding took more time in months or weeks. But as compared to coming to additive manufacturing, the additive manufacturing, right from the layout to the manufacture of the final component, it will complete within days. So that type of advantage we have through additive manufacturing. And we have seen additive manufacturing process cycle right from the design optimization simulation to post-processing and monitoring a validation of the component. And material selection is, we have discussed the material selection based on the product requirement and final functioning of the component is very important. And manufacturing of the component and process parameters and the environment is very taking keen important role in the fabrication or the preparation of the components. And the post-processing is the essential step in additive manufacturing process cycle. And we have seen the various levels of the additive manufacturing from right from the level 1, that is from the directly manufactured low volume parts are directly manufactured from CAD file to the new product design added value to the offer mass production. So we have gone through the levels of additive manufacturing, and we have seen the various types of additive manufacturing process: VAT photopolymerization, material jetting, powder bed fusion, and direct energy deposition, binder jetting, material extrusion, sheet lamination, etc. And what are the materials, raw material form required are also we have seen. And this is a second session. We are continuing the second session. The topic of the second session is additive manufacturing processes. In last class, we have ended the session 1 with the classification of additive manufacturing processes. And now we are continuing the additive manufacturing processes in session 2. I once again welcome you all to the additive manufacturing processes, that is the dealing or the discussion topic under digital manufacturing course. So myself, Dr. ANANDA BABU, Associate Professor, Department of Mechanical Engineering, Nadimpalli Satyanarayan Raju, Institute of Technology, NSRIT, Sontiam, Visakhapatnam. Now we will move to the first process of additive manufacturing. The well-known additive manufacturing process is VAT photopolymerization. The VAT photopolymerization process can be defined as an additive manufacturing process in which the liquid photopolymer, which can be hardened or cured, by light activated photopolymerization. In this additive manufacturing process, the VAT photopolymerization, the photopolymerize, the the liquid polymers are subjected to the light, UV light, or to cure or harden based on the scan of the UV light, which comes from the design of the component. So in this VAT photopolymerization, the various well-known processes of VAT photopolymerization techniques are the stereolithography, SLA, and second one is digital light processing, DLP. This stereolithography process and DLP, digital light processing, comes under photopolymerization. In both the processes, stereolithography, SLA, and DLP, we are using the polymers which can be done the chemical reaction under when it's subjected to light source, under the range of 10 to 400 nanometers UV light. And in recent times, the photopolymerization is also performed at the visible light range also. Now we will see what is photopolymerization, what is stereolithography, and what is digital light processing. As you see here in this figure 1, stereolithography, the build plate and liquid resin and support structures, scanning mirror, and laser source. We are seeing all these, the schematic representation of the stereolithography and what are the various parts involved in the stereolithography. In VAT photopolymerization technique, SLA, the polymers which can be cured or hardened to develop a 3D model, 3D object, three-dimensional object, right from the three-dimensional model, CAD model, is in this process, the liquid photopolymers are placed in the vat, As shown here, this is the vat, and the liquid resin is poured in this vat. And this is the build plate, and the laser light comes from the bottom of the vat, and the scanning mirrors help to direct the laser light based on the G-coded program, which comes from the slicer. Before, as you know that the additive manufacturing process cycle, the additive manufacturing follows some process chain. In that process chain, the pre-processing is very important point. This pre-processing plays a major crucial role in which we have designed and optimized and simulate the CAD file of the component which is to be produced. So in pre-processing only, while preparation of the CAD model and while preparation of the slicing object, slicer software, we are able to convert the model STL file format to the G-coded file. So the G-coded file is transmitted or sent. The G-coded program is sent to the system, and based on that commands, based on the program, the laser light injects onto the vat in which the liquid resin is placed. Based on this programmable G-coded program, the laser light and the mirror, the scanning mirrors moves, and the three-dimensional object is obtained by the laser light, which projects onto the liquid resin through the scanning mirrors. And here, whatever the digital light processing whatever the digital light processing we are seeing here, in as compared to SLA, the digital light processing is quicker because in SLA, the laser light scans, the laser light raster scans point by point in scanning manner. But here in digital light processing, the total area, the total layer itself, once even at a point of time, the total layer is cured because of the light source projected through the projector. So this is the major difference between the stereolithography and digital light processing. As compared to the stereolithography process, where the laser light scans and passes as a raster scan, it took more time to complete the product. And in this digital light processing, the complete layer cured or hardened when it projects the light source. So this is the major difference between SLA and DLP. And after completion of one layer in SLA and DLP, there are 2 points, top-down approach and bottom-up approach. The top-down approach or bottom-up approach, whatever may be the approach, the layer, whatever the layer cured is more upside, and the next layer comes into the next uncured filament comes below beneath the already cured or hardened layer. Like that, every layer comes and the build plate moves up or the VAT comes down based on the approach, and the three-dimensional object is printed. The three-dimensional object, physical object, can be printed through the last raster laser scan or the projector of the light. So in DLP, now we will see the working principles of the VAT photopolymerization. The first step is the conventional scanning type of SLA process uses this stereolithography. SLA means the stereolithography, which is the basic 3D printed or the additive manufacturing processes or the rapid prototyping process, in which the UV laser beam is scanned and cure the surface of the photo curable resin. As I told earlier, the filament, the resin which is placed or the poured in the vat is the photo curable resin, and this UV laser scans layer by layer and cures the surface of the photo curable resin layer by layer. While in DLP, digital light processing, the projection type, the total layer, once the light projects onto the vat, the total layer in the DLP is hardened. So the projection type DLP process utilizes an LED light to project a whole cross-section area of mass projection onto the resin surface. The main difference between, we can analyze the main difference between SLA and DLP is the approach, the way of the light projection. In SLA, the beam, the UV laser beam scans the surface or cross-section. In DLP, the LED light, the light, it covers at a time the total layer. That is the main difference. And the second point is the photosensitive resins are mainly acrylic or epoxy-based monomers. Whatever the resin we are utilizing in this VAT photopolymerization is the acrylic or epoxy-based monomers, which can be done a chemical reaction, which can be subjected as a chemical reaction. When it's subjected to, it can be the epoxy-based monomers or the acrylic-based monomers, or can be hardened or can be form a chain type structure while the photopolymerization. That's why the second point says that the photosensitive resins are acrylic or epoxy-based monomers, and polymerization chain reaction. When the light source injects onto the photocurable resin, the polymerization chain reaction occurs and it solidifies. And due to this chain reaction, the polymerization chain reaction solidifies a resin layer, solidifies and forms a solid structure. So when it is subjected to light source, the wet photopolymerization process can be operated, as I told, in two mechanisms. One is top-down configuration, in which the laser scans from the above. In top-down configuration, there are two mechanisms in wet photopolymerization. One is top-down approach. Second one is bottom-up approach. In top-down approach, the laser scans from the top, from the above, and the build plate is lowered after curing each layer. So when the laser scans from the top and the build plate, when it scans, when the laser light scans the one layer of the resin, then the build plate moves down for the next layer, like third layer, and the remaining all layers will be cured when it's subjected to light source, UV light source. So in top-down configuration, the laser light scans from the above. This is the position, the orientation of the laser light comes from the above, and the build platform, which is having the wet and the photopolymer, the polymer monomers resin is moved downwards, that is lowered after curing each layer. And in bottom-up approach or configuration, the resin is cured from the transparent base of the vat. This is the vat. We consider this is the vat. Vat is placed like this. The vat is placed like this, and the laser light transmits from the transparent base of the vat. The vat is filled with the resin or the photocurable resin, and the laser light is transmitted through the transparent base of the vat, and the build plate is raised after one completion of the layer. So in top-down approach, the laser light or the light source is placed at the above, and the build platform moves lower side. And in bottom-up approach, the resin cured moves upward, and the laser light is placed at the bottom of the vat, and the light source is transmits through the transparent base of the vat, and the platform is raised after each layer. So in earlier case, in top-down configuration, the build plate is lowered or moved upwards after one completion of the curing, after one completion of the first each layer. And in bottom-up approach, the vat is moved upward after completion of one layer. So like that, the process continues. And the fourth point, the resin flows in after each adjustment of the build platform, and the process repeats. The light source or the raster or the DLP is the repeats. The process repeats until all layers have been built till the completion of the product. And fifth point, upon completion, the printed part is elevated from the vat. Upon completion, after hardening or curing of each layer, the printed part should be elevated from the vat. As you know that in raster scan type or the DLP, direct light source, the portion which is to be printed or hardened or cured is transmits to the solid form, but we have the surrounding portion, we have the untreated or uncured or unreacted resin that should be that should be washed away from the vat. And this process is carried out using isopropyl alcohol. So after that, after preparation, after scanning, after completion of all the layers, after completion of curing or hardening of all layers, the product which is prepared through vat photopolymerization should be gone through post-processing. The post-processing using a UV oven is required. So whatever the product prepared or whatever the product printed or cured or hardened, whatever the product we got through vat photopolymerization should be undergone through post-curing process, in which this post-processing is carried out in UV oven to ensure that the printed parts are fully cured to achieve the desired mechanical performance. What happens in the process is, while the raster or the direct light source, the UV light or the LED light is projected on the resin, and each layer formed, and the next layer, each layer is formed, and the bonding between each layer forms once, or each layer forms are based on the raster, and the next layer, after completion of one layer, as you know that the vat has to be lowered or upward to get the second next layer. But the thing we have to remember is, what about the welding, whatever the cohesive forces, whatever the cohesive bonding between first layer and the second layer and the remaining layers. So through this post-processing of the product which is cured in vat photopolymerization, and in order to achieve the desired mechanical performance, this post-processing is very, very essential to get the final desired characteristics of the item or the product. And the benefits, the various benefits are there with this photopolymerization, vat photopolymerization additive manufacturing process. And the first benefit is, the vat photopolymerization technique provides the highest accuracy, excellent surface finishing, and fine details can be obtained. The very fine details can be obtained. As you know that it is a light source, the resin subjected to UV light or LED light, we can get the fine details of the keen observation of the fine details, even in SEM or optical microscope, up to the fine details we can create through this vat photopolymerization up to 150 micrometers. 150 micrometers. As you know that human hair size, our hair size is around 70 microns. So you can assume we can prepare the components, we can prepare the items with the 150 micron size, and we can get the excellent surface finish and highest accuracy in the fine details, also the fine details. So that is the important parameter, important point or benefit we can achieve through this vat photopolymerization technique. So, and second benefit is, large objects also we can get, but the thing is, it takes more time. The things are more time, and SLA or DLP, stereolithography or digital light processing parts are highly isotropic due to continuous polymer network. As I told earlier, the monomer, whatever exists in the polymers, are subjected, when those monomers or the polymer subjected to UV light or LED light, The continuous chain structure will come in all the direction, X, Y, and Z directions. Therefore, we can expect more isotropic nature in the around the solid, in the component which is obtained through this SLR DLP. That's why the high isotropic nature is observed in the components printed or the obtained through SLR DLP because of the cohesiveness between the layers. And open system of an accessible resin vat allows for the ease of material removal. So the vat is opened like this. So we can easily remove the completed component from that particular portion. And bottom-up configuration process uses lesser amounts of resin, which makes more economical efficient. And whatever the bottom-up configuration we have discussed, the laser light or the LED light projection comes from the bottom, and the surface, the elevates the product, the platform elevates like this. And therefore, through this bottom-up approach of the configuration, we can get the component and with the less amounts of the resin. That means we may not waste the uncured resin. So this is very important process point in the VAT photopolymerization. Even the benefits of the VAT photopolymerization are more, we are having some drawbacks. The manual removal of the support structures. As you see here, this is the component we have to prepare through the VAT photopolymerization. But to get this structure, to get this shape, we have to provide in pre-processing stage, we have to provide the structures, the support structures, while the pre-processing stage continue before the processing stage. So in pre-processing, as you know that the additive manufacturing process chain, we have pre-processing stage, processing stage, and post-processing stage. In pre-processing stage, we have to design the component, and we have to provide various parameters before processing the component. And this pre-processing involves the provision of support structure and the layer height, wall thickness, and all the details of the layer height, wall thickness, the structure, the infill density, like that. Many parameters are there. The support structure pattern also important parameter. So the manual removal of the support structure for overhanging features can be tedious and time consuming. Even we can produce the every critical or any critical objects through this VAT photopolymerization. The thing is, the removal of the support structure is very tedious and time consuming, and sometimes the main required part also may be damaged while removing the support structure. And second point is, the post-curing process for complete curing and stability is required. The post-curing process of the complete part is required, especially the functional resins for engineering and mandatory for dentistry and jewelry applications. The very important point is the VAT photopolymerization technique is very useful in dental field, dentistries, and jewelry application, jewelry field. But important thing is, every part of this product has to be post-processed perfectly. Otherwise, the portion which is not cured perfectly or not undergone through post-processing efficiently, it may cause the damage of the component. And next drawback is the range of photopolymerized materials. The range of materials for the VAT photopolymerization process are very limited material types are available for this SLA and DLP process. This is the very much limited, more considerable point, and we may expect the various startups or entrepreneurs or the industry persons will come up with the new photopolymer materials to engage or to provide the flexibility to this photopolymerization process. And a strong addition between cured layer and the build platform, the total structure is formed on the build platform, as you know that. So the addition between the cured layers and the build platform also is very important point. If you want to remove the structure, if you want to remove your material from the build platform after completion of every structure, every part of the process, if it is not delaminated, if it is not removed from the detached from the build platform, what is the use? So the detachment or the delamination of your component from the build platform is also important parameter. And sometimes during this removal of this part, removal of your component or removal of the support structure from the build platform, your structure or your component may be damaged because of this addition between cured layers and the build platform. And we can see here various range of materials available for the VAT photopolymerization. These are the various range of materials available for photopolymerization technique. And the various applications of this additive manufacturing process can be this manufacturing process. This additive manufacturing VAT photopolymerization is used in various fields, automotive fields, sports equipments, and biomedical engineering point of view, and engineering implants and bone regeneration, high strength applications, EMI shielding, flexible electronics field, strain sensors, micro actuators, lattice structures. For so many applications, this VAT photopolymerization technique is used. We can say that this VAT photopolymerization is high in functional prototyping and the preparation of the molds for casting products, patterns of jewelry and audiology. And this process is used in dental applications such as dentures and aligners, and healthcare, medical applications, and so many purposes this VAT photopolymerization is used. And second process is material extrusion. As we seen earlier, the VAT photopolymerization, the raw form of the VAT photopolymerization, the source of material is the liquid. In material extrusion process, the raw form of this material is the solid. In VAT photopolymerization, the raw form of the material used in VAT photopolymerization is liquid form, and in this material extrusion process, it is in solid. As you know, here the material extrusion process are commonly referred to as fused deposition modeling or fused filament fabrication. So material extrusion process are also termed as fused deposition modeling and fused filament fabrication, triple F. And FDM is the second most widely used rapid prototyping technology after this VAT photopolymerization. The very limitation which creates the challenge for the wide application, wide publicity of this or wide usage of this FDM is earlier there is some patent issue. So after expiration of the FDM patent, more number of entrepreneurs or more number of industries from various locations around the globe, various parts of the around the globe are now preparing the FDM machines, and now the FDM machines are available at the low cost, even at 15,000, 20,000 or 30,000 from hobbyist to the industry purpose. And this is the fuse deposition modeling equipment, PROSA. And this is the schematic representation of the extrusion process. Here, this is the red portion is the polymer filament. The polymer filament. And here we are able to see the bearing gears and transmission gears. And the filament is passing through nozzle holder. And the filament is heated in the hot chamber. And this hot chamber or heater is connected with the thermal sensor. Through this, we can set the temperature of the hot end, and the semi-solid, semi-melted polymer comes from the hot end, is laid down on the platform or the bed based on the commands received from the G-coded file, which is prepared as a part of pre-processing. And now we are able to see the working principle, how it works. The solid thermoplastic filament are wound on a coil. As you see here, the filament is wound on a coil, and this filament is fed into an extrusion nozzle through the hot end, and it can activate and disable the flow of materials. A numerically operated mechanism using a stepper motor or servo motor directs the filament through the hot end, which follows the CAD file and enables the nozzle heated head to be moved through this bearing gear and transmission gear in vertical direction. The filament is heated in semi-liquid state. When the filament enters into the hot end through the heater, the filament is heated into the liquid, semi-liquid state, and this transmission gear and bearing gear are moving, are forcing the semi-liquid state filament to the hot end, to the bed, and the nozzle through the nozzle, and the semi-liquid resin or semi-liquid filament is deposited under the bed build platform layer by layer. A thin layer cools and solidifies. If you see, there is a fan, there is a small fan which uses to solidify the layer depicted or deposited on the build platform. A thin layer cools and solidifies while binding to the layer beneath it until the build platform is completed. And after completion of one layer, the the hot end or the extrusion mechanism is move upward, or the build platform moves downward based on the equipment and projection program instructions. And next step is the program instructions, which comes from the G-coded file, which has prepared through the CAD model using the computer system and softwares like slicers. 3D printing slicing softwares are fed into the machine, and based on the commands only, based on the instructions only, the bed moves downwards, or the extrusion mechanism moves in the upwards in Z direction. And there is important point of the process parameters or the environment to be noted here are the layer thickness of the filament laid on the build platform, and width of the filament, and orientation of the filaments, and the air gap between the filament to filament. They present in the same layer, the air gap between the filament to filament. If one layer, if one scan, one part is laid down on the platform, and if the second layer, second line is laid down like this, and the air gap between these two rasters plays major role. So we have to avoid this air gap between the rasters. And the key process parameters, the layer thickness, width of the raster, and orientation of the filament, and the air gap between each raster are the key processing parameters that influence the mechanical properties of the printed FDM parts. FDM refers fused deposition model, fused deposition modeling. So to prevent warping, what is warping? These are the warping faults. These are the warpings of 3D printed object. So this here we are able to see the bottom layer, which is at to be addition to the build platform is moves upward. So this is the warping. This type of faults observed in 3D printing are termed as warping. And we are able to see, here also we are able to see the warping at the edges. The main point to be observed here is the warpings are observed at the corners or edges of the object. So to prevent warping, large flat areas should be avoided, and fillets can be added in sharp corners. Instead of these sharp corners, if you provide fillets, we can get satisfied prints, and we can avoid the warping defects. And the FDM parts having more flexibility in terms of benefits. So FDM parts and FDM can be done at a low price, and the machine costs around 30,000 or 15,000. We are able to purchase at the lowest price from 15,000 to any price we can get. This is one of the most benefited parameter to the hobbyists and who are interested to learn from the basics. And the high speed as compared to the VAT photopolymerization, the FDM parts can be prepared at a high speed, and simplicity of the process. Just after pre-processing, we can load the program, G-coded program into the machine, and we can just insert the filament to the nozzle, and the machine can run as per the program very efficiently without more human interaction. That is the simplicity we can observe in fused deposition modeling. And because of this simplicity in operation, FDM gets more focus of the present scenario. The FDM printers are office friendly, quiet, and easy to set up, and it practically requires only electricity and raw materials and a computer. With very limited sources also, we can prepare FDM prints, 3D printed objects through FDM at low price and at low space, and there is no requirement of big surface, big space for these machines, and we can prepare at high speed. FDM is reasonably quick in production as compared to VAT photopolymerization. This FDM is quick for small pieces in order of the few cubic meters. As you see here, FDM fused deposition modeling printer, FDM technique can be used for any critical structure. But the main important parameter we have to observe is the raw material form. In the raw material form, in the VAT photopolymerization, the form of the raw material is in liquid state, and in the FDM, the form of the raw material in the solid state, in the filament form. So FDM printers are widely available with the ability to build fully functional parts. Fully functional parts can be prepared based on the requirement to remove or to avoid the time lapse in the production. And there are some drawbacks in every process as VAT photopolymerization. Here also, in this additive manufacturing process, so we have some limitations. What are the limitations? The limitations are the accuracy and fine details of the FDM parts are less. But in VAT photopolymerization, we can get the more fine details, and we can expect more superior accuracy in VAT photopolymerization because of the mechanism involved. But here, the FDM gives the low accuracy, and we may not get fine details as in VPP, VAT photopolymerization. Due to the discretized layer by layer printing process, FDM parts are having stir-stepping surfaces which lead to the surface finish, rough surface finish. In VPP, the structure is having continuous structure, but here the surface finishing is not up to the mark. And the mechanical properties of the FDM parts are less due to the anisotropic nature in vertical direction. One layer laid over the other layer, like that all layers printed in this manner in Z direction. But if you observe here, the anisotropic nature, what is the main difference, main drawback in FDM parts is the weak in mechanical properties in vertical direction. Therefore, even we get the isotropic nature in horizontal direction, but in the vertical direction, between the layers, we may not expect the isotropic nature in the mechanical properties. That will be the important point to be noted before get into the FDM printing. So this is very important parameter, and further post-processing is very much required after printing to remove the support structures. If you see here, the product is this one, but the support structures occupies more space. And here, if you want to remove these support structures, it took more time, and the more focus of the operator or the person is involved, and sometimes during the removal of the process, during the removal of the support structure, the main parts also damaged. So the support structures that are fabricated for overhanging geometries can be removed manually by breaking them away, simply washed away for water-soluble support materials. So new techniques come into the picture like water-soluble support structures, but in some cases, the removal of the support structure is a tedious task and the important considerable point. And the various range of materials available are for the material extrusion process are tough materials, flexible materials, flame retarded materials, and particle filled materials like that. So very famous material in the FDM processors, in the FDM process or the material extrusion process is polylactic acid. polylactic acid material is using in high level and more production, the PLA material is used. And for high strength, we are using ABS. And for flexible purpose, flexible prints, we are using the different TPU, flexible and rubber-like structures. We can get the TPU and polypropylene and like nylon we are using. And so many materials are listed here, which are used for the material extrusion process. And the fuse deposition modeling parts are used in various applications, like from biomedical applications, automobile applications, aerospace and aircraft industries, household applications, sports and equipment, music equipment, and the number of applications the FDM prints are used. So the conceptual modeling and rapid prototyping, the main applications of FDM printed parts is rapid prototyping and concept modeling. Architectural models can be prepared and marketing and graphic designs can be done, and footprinting also the new technology which is coming into the market. We can print the food items based on the geometry of the file. We can create different structures, and footprinting is the new technology coming to the environment using this fuse deposition modeling. And I'm happy to show these all images, the gallery of 3D printed items, the gallery of 3D printed items in 3D printing lab at NSRIT. So we are seeing here various items right from the mechanical structures, the architectures, and the customized objects, and the items which can be used in medical fields and schools to demonstrate the human body or the organic structures, and different types of components can be organic models and inorganic models. Different structures can be prepared or fabricated or designed or developed using fuse deposition modeling technique, which is available in 3D printing laboratory in NSRIT. These are all the models prepared in our laboratory only. And we can prepare, these are the various important types are the models we have prepared in 3D printed laboratory in mechanical engineering department, NSRIT. We are developing 3D dual names, three-dimensional dual names in one block only. We are having two names. One side, it appears one name, and in second side, it appears as second name. And we are preparing, our students are doing project works, more interesting project works, 3D statues or miniatures or face bust models from the 2D photos, and phone stands, customized more products, and 3D mementos. We are designing and developing 3D mementos and awards, and 3D tools. Whatever the components we are developing, we are preparing in modeling as a curriculum. We are preparing here the 3D printed models from the knowns 3D printed models, 3D models, CAD models. And we are preparing 3D photos and 3D architectures and 3D keychains and name plates, and so many types of variety of materials, variety of products are developing in 3D printing laboratories, which is situated in mechanical engineering department, NSRIT. And these are all the facilities available in NSRIT, the 3D printed laboratory and CNC milling machine and robots, applied robotic laboratory. And these are the important hands-on experience sessions are conducting regularly to enhance the technical skill of the students in NSRIT, in mechanical engineering department and other departments. and various laboratories we can see here. The laboratory facilities are available at a large scale, and various experts are also visiting our facilities and giving their valuable suggestions to improve these facilities and to exhibit more and to get the more attention of students and researchers and more industry and academia. And various interdisciplinary projects are done by the students. And about this department, our department, the department is established in 2009 in NSRIT, Nadimpalli Satyanarayana Raju Institute of Technology, which is affiliated to Jawaharlal Nehru Technological University, Gorajada, Vizianagaram. And we offers UG and PG programs. UG program BTech Mechanical with 90 intake, and PG program MTech Thermal Engineering with 12 intake. And we are having sufficient faculty members and number of doctorates. The number of doctorates are 5. Myself, one of the doctorate, Dr. ANANDA BABU, and the Nandipalli Satyanarayana Raju Institute of Technology, NSRIT, offers BTech programs, civil engineering, computer science engineering, artificial and machine learning, and CNC, computer science engineering, data science, ECE, EEE, and mechanical engineering. And we are also offering programs, regular manner, honors and minors with transdisciplinary applications and with more industry institute linkage. And this session will continue tomorrow. We will go through remaining process, remaining additive manufacturing classic process, and we will continue tomorrow. And these are the references I took from the textbooks or the website, YouTube or websites for your reference. And thank you. And I want to show the various 3D printed objects printed in our mechanical engineering 3D printed laboratory. These are the components we are prepared. Our students are preparing. The students are designed as a part of CAD lab, and the products are saved in .stl format. After completion of the slicing, the G-coded files of these products are transmitted to the 3D printer, and by giving the number of, by changing the, or by setting the properties, the various processes, parameters like layer thickness, wall thickness, infill density, support structure pattern, and infill density pattern, and temperatures of the build plate and nozzle, our students of mechanical engineering department, NSRIT, and other students also doing, other students of NSRIT are preparing this type of structures, mechanical structures or industrial products at their own hands-on experiences, and these are all these mechanical related components are prepared by our students. I am very proud to say our students are preparing, and these knuckle joint parts, parts also preparing by our students, and this gyroscopic and this gyroscope components also prepared by our students, and radial 7 radial cylinder prototype also prepared here in our CAD lab only, and model CAD lab and printed in 3D printing laboratory. And these are on the gears. And some industries also approaching us to provide the 3D prints like other institutions, like other industries. Some institutes or some industries are approaching for 3D printing services, and we are happy to share we are providing the services our expertise to the various industries, and we are also preparing the small products or small miniatures for the biogas plants and the bio toilets. And I am happy to share the NSRIT Mechanical Engineering Department students are utilizing the internet sources and developing and observing and finding various resources, and we are developing the components of organic structures of human body for the usage of teachers, for the benefit of teachers, to explain more in detail to the school students. And we are preparing these all structures of heart. This is heart structure. We are prepared. Our students are printed in 3D printed laboratory, and we are recently our students are prepared this GSLV prototype launched by ISRO. And finally, I want to say with more pride and happiness, our students are preparing this type of organic structures, of human face from 2D photos. So the 2D photographs, this is my 3D printed model, bust model of face model of mine, and I am happy to share this. These all structures few are designed and developed by our students, and few models are downloaded from the internet sources, from various internet sources, and our students getting more hands-on experience in this 3D printing laboratory. And I'm happy to share our students are more interestingly participating in 3D printing laboratory at every point of time, and they are gaining more knowledge from 3D printing laboratory and robotics laboratory and CNC machining laboratory and mechatronics laboratory. And all the students in NSRIT are actively participating and learning more and having and practicing to get the hands-on experience. And with this, I'm concluding this my second session. Tomorrow at 11 o'clock, we will meet one more time and to deliver and to discuss the further 3D printing additive manufacturing process tomorrow. With this, I am concluding my session. I hope you learn various 3D printing additive manufacturing process, VAT photopolymerization, and material extrusion, that is fused deposition modeling in today's class. In next class, we will discuss further. Till then, have a good day. Goodbye. Thank you. Namaste. Namaskara.